In the last video, we learned about the law of sines. It was something kind of similar to SOHCAHTOA, but it worked for any triangle, not just right triangles. In this video, we're going to learn about the law of cosines, which is going to be very similar to the Pythagorean theorem, except once again, this will work on all triangles, whereas Pythagorean theorem only works on right triangles. So if you think about Pythagorean theorem, it's normally like a squared plus b squared equals c squared, and that's exactly what you would have here, and that's what happens when you have a right triangle. But if you don't have a right triangle, then you have this extra term here, minus 2ab cosine of the angle c, and this is the law of cosines that can be used to solve more triangles. In the previous video, we saw an example of solving a triangle that was of the ASA type. That was angle, side, angle. In this video, we're going to solve one of SAS, or side, angle, side, as well as one of the SSS, or side, side, side. So these are two new types of solving triangle problems that we can use the law of cosine to get our answer. So let's take a look at the first one, the side, angle, side. So we know one side A is 5. We'll call this side A is 5. B is 7. And the angle C, which is between them, is 40 degrees. So we have side, angle, side. We cannot use law of sines here, because if you were to write out the three different possible equations for law of sines, every single one of them would have two knowns and two unknowns. You can't solve and get the one missing unknown. However, if we use law of cosine, we're going to be able to get the answer to this problem. So we start out by saying, okay, we have my A and my B and the angle between them. So we're going to use law of cosines here. So it says c squared is a squared plus b squared minus 2 times a times b cosine of the angle between them, cosine of 40 degrees. So we put this in our calculator here, 5 squared plus 7 squared minus 2 times 5 times 7 times cosine of 40, and I'm getting c squared is 20.3769, and if you square root that and round to one decimal place, I get 4.5. So we found the missing side of this triangle, and once we have that missing side, then we can go ahead and finish the two angles that are missing. And we could use law of cosines to find the angle, but we can also use law of sines now. So I can do sine of the angle 40 divided by the side opposite, which is 4.5. We know that now. Is sine of angle A, let's say, over the opposite of A is 5. So then I would have sine of A is 5 sine 40 over 4.5. Sine of A is 5 sine 40 divided by 4.5. I'm getting 0.7 here. And if I do my inverse sine on that, I get 45.6 degrees. And I can get the last missing angle, same thing. Sine of 40 over the known side, now 4.5. Sine of B over the known B side of 7. And I'll skip a little bit of the work here. It's just the same thing, I'm running out of space right there. So we'd have 7 times sine of 40 divided by 4.5. And then do sine inverse of that. And I'm going to B, which is 89.2 degrees. And now we have our missing sides and our missing angles. So we can just double check here that we didn't make any mistakes anywhere. So let's say, looks right here. You may notice something. You may notice if you added those three angles, you do not get 180 degrees. 40 degrees plus 89.2 degrees plus 45.6. This gets 174.8. So this is going to happen on these problems because as we're doing things, we are rounding our answers. And as you round your answers, it means the answers are not exactly right. And that means your angles are not going to be exactly right, which means that they're not going to add up perfectly to 180. If I had chosen to round to say 2 or 3 or 4 decimal places, and I'd done this, they probably would have added up almost exactly to 180. So it just comes down to the fact that we are doing approximates, which means our answers are not perfect, which means they're not going to work out exactly to 180 degrees. So don't get too hung up on that. Just follow the math, get the answers, and you'll see what you get. Now this second problem here is a side, side, side type. So this time the three things we know are all sides. We have one of them is 10, the other is 8, and this one's 14. So we don't have any angles. We can still use law of cosines. Law of cosines says c squared equals a squared plus b squared minus 2ab cosine of the angle C, which we don't know, so that's going to be our one unknown here. So we're going to get 196 equals 10 squared plus 8 squared is 164 minus 2 times 10 times 8 is 160 cosine C. We're going to subtract the 164 from both sides. And we get 32 is negative 160 cosine C. We go ahead and divide negative 32 by 160. And we get negative 0.2 here. Then if I do cosine inverse of this, and I am actually going to use the negative number here because I'm not trying to find the reference angle, I'm trying to find the actual angle. I'm getting 101.5 degrees for angle C. And once you have one piece of information from law of cosines, we can switch back to law of sines now. So sine of the angle we now know, divided by the side opposite, is equal to sine of angle A over the side 10. So we'd have sine A is 10 sine 101.5 over 14. Sine A is 10 sine 101.5 divided by 14, and sine A is going to be like 0.7. If we do our sine inverse now, we get 44.4 degrees. And if I use law of sines one more time, known angle divided by opposite side, sine of unknown angle B over opposite side that. Again, same kind of steps here. 8 times sine of 101.5 divided by 14, and sine inverse that, and I get 34.1 degrees. And let's just check these angles here. 101.5 plus 44.4 plus 34.1. And this time they do add to 180. So my rounding didn't actually hurt me here in this problem. But the idea with law of cosines is you use your law of cosines to find one missing piece of information. And then once you have that, you can switch over to using law of sines to find the remaining pieces of information that are missing. Now you could continue to use law of cosines to find all three. It's just law of cosines usually takes more work than law of sines. That's why we like to switch over to law of sines. But hopefully this gives you more ideas of how we can use law of cosines in order to solve our